this one will be your yield. So this one will be your stress strain curve. So again, where do you get this one? You don't get this one from analysis. You get this one from testing. The tensile testing that I've just shown you, or probably have done that in Polytechnique, right? Tensile testing. So from there you will be able to get your stress strain curve. So how do you bring this knowledge now to mechanics? It's simple, right? You get your principal stress if this one is lower than ultimate. Say if you're just doing a design and you don't want your design to fail, you have a safety factor. So I'm sure you have done this one already. So you know your safety factor. How do you determine your safety factor? There's so many tables, so many references to get that. Depending on the type of your loading, depending on the conditions and so on, you will be able to get your safety factor. If you're a designer, you will be able to find your way how to determine that safety factor value. So this one, we either calculate using the elementary mechanics and calculation, or finite element if the structure is complex. Right? Probably a simple beam, we can calculate the stress, but if it becomes a chair like that, then it becomes quite difficult, and let's simplify it. So you have to use finite element just to be able to know where the critical section is. Of course, using finite element for this one is really an overkill, so most likely more complex structure with finite element will be useful. So what we're doing at the moment is just, we have our state of stress. Everybody knows that already. Our state of stress is that we're going to be stressed. And then from there we will be able to calculate this one. And once we calculate this one, the reason for using this one is we just want to know that structure, that material, that design will fail. This one is good for brittle materials. And of course, we have undergone we have discussed about the von Mises stress. So what about von Mises stress? That's applicable for ductile materials. So instead of SU, you compare that with your yield. Yeah? So these are your failure theories, static failure theories. So we have a lot of failure theories. I don't know if you have discussed the different failure theories in your mechanical design. So there are different types of failure theories: cracking, fatigue, static failure, or high displacements, or high yield, so on and so forth. So at the moment, the failure that we're looking at the moment is just static failure. We haven't discussed about fatigue yet, and that's a more complicated process. So this one is the principal stress, or the maximum stress criteria, and this one is the octahedral failure criteria. Principal stress criteria, or the maximum stress criteria, and then we have your octahedral or shear stress criteria, or octahedral stress criteria. So these are the two failure criteria. Are there any more? Well, there's a lot really. For the next one, so you know how to get this one, right? So again, we have now your state of stress, sigma. So you will be able to have your sigma 1,1, sigma 1,2, sigma 1,3, and we know that this one now is symmetric. We have proven this one. Okay? And then this one will be equal to, just do a transformation so you can get your principal stresses. Yes? So that's how you get this one. Of course, you get sigma 1, sigma 2, sigma 3. Also by using this one, you will be able to solve for your von Mises. Again, there's a correction there. I think everything must be positive in there. Please correct me from my equation that I gave you last time. Your von Mises must be 1 over square root of 2, yes? And then sigma 1 minus sigma 2, that square, plus, so everything is a plus. I think I made somewhere wherein I place a negative value here, sigma 2. And this one is it a plus or minus? Minus 6. And then we have your sigma 1 2 squared, sigma 2 3, sigma 1 3 squared. Okay? Is that okay? So I think I made some mistake in the equation for the von Mises stress that I gave you. Please check, it's in your notes anyway, so you can always compare. So this is how you get your sigma von Mises, and this is how you get your principal stress. Now the question is, getting these values, right? If they are not given, then your question will be identifying this one. We had already a deep problem, and we were able to identify, from a deep problem, we were able to identify your normal stresses and your shear stresses. So you put it in, and then you calculate your principal stress. Yes? So that's how you determine whether your material, structure, or your design is safe. As simple as that. So any changes in geometry, like what you're doing in design, or any changes in material, will definitely change the stress acting on your material.
Please correct it.
Yes, because all of these will also be dependent on the material and geometry. So that's why you're changing the design to be able to reduce the stress. And then if you get this stress, you compare it with this one here. So that's basically a very, very common procedure in the process of doing design. Now, there are still a lot of criteria, so one of them will be fracture mechanics. So at the moment, I'm just going to present you, or let's just solve a brief for some problems in fracture mechanics. Not so difficult, really. Because I want to relate this one to pressure vessels as well. Although, let's learn this one for the sake of knowledge, but of course, if it comes out, then at least we know what's going on. So this one has to do with the application as well. You have to solve for the principal stresses first before you can even apply the theory of fracture mechanics or your fracture mechanics failure criteria. So let's have a look at question 23.6.6.
One. 46.
Yeah.
Okay, really at 6. You don't need to copy. Don't copy. That's what I use. Somewhere.
I'm just writing the problem here. The fracture toughness is given by KIC. So KIC is also a material property, fracture toughness. So it's the same as the yield strength or ultimate strength. So this one is a material property. Once we say material property, it can only be determined by testing. So that's a material property. Everything has a material property. And you can only define these material properties by testing. So we're going to compare this material property with the so-called stresses or whatever forces acting on the body, and then we're going to compare whether our system is safe or not, or we can at least here, in this case, we can determine a critical crack length A. So let's have a look at this one here. The fracture toughness of the ceramic is given by this one here. Sigma 1 equal to pi A equal to 24 megapascal per square meter. Determine the critical crack length A for a component subjected to a stress. So this is now our state of stress, wherein one of the principal stresses is equal to 200 megapascal. So the problem here is not determining the principal stresses, it's really analyzing. The question here really is, what is that minimum crack size that can be present in our structure and we still know it's safe to work? So it's not just a matter of calculating the principal stress, because that's quite elementary already. It's really trying to understand the problem. What does this problem mean? We're actually determining that minimum crack length A that can exist in this ceramic, and then it can still function properly. That's the meaning of this problem. So, let me further explain that. So, this is your material, and there will be a crack length A. It's not actually a crack length, but it's half the crack length. And what will cause this one to grow? What type of stress will cause this one to grow? So again, you have to go back to the definitions of your principal stress. Which stress will affect or will cause the crack to grow? Now take note, sigma 1 is pure tension, sigma 3 compression, sigma 2 in between. Sigma 1 is the maximum because it will create an extension. So which one here will be the stress that we're going to use in the analysis? Sigma 1. And we're assuming that sigma 1 is acting perpendicularly to that crack. Right? So we're not just doing any mathematics now, we're just really trying to analyze this problem. And that's the beauty of mechanics, wherein you can apply these principles to practical problems. So that one of the failure criteria is that this one here, stress intensity factor, I won't say much about that. Stress intensity factor must be lesser or equal to your fracture toughness. So that's one criteria. Remember, we had a criteria, right? Another failure. The first two failure criteria that we studied are sigma 1 less than this SU all over N. And then your bone knee stress must be less than SY all over N. That's two failure criteria already. The other failure criteria that we're looking at is fracture mechanics, wherein this stress intensity factor must be less than or equal to this fracture toughness, which is a material property, just like SU or SY. And then, of course, this can always be determined by test. So in this case, our KIC is given to be 24 megapascal square root of a meter. Yes? So, like I said, this can be determined by test. So with that, you will now be able to solve for sigma 1 here. Of course, by doing so, you can have your so-called sigma. So what's the equation like here? Sigma cube minus I1 sigma squared plus I2 sigma minus I3. This is equal to 0. So you can now solve for I1, I2, I3. So what are I1, I2, and I3? These are invariants. So how do you solve that? We have an equation there. So I won't be writing this one too much of this one. So you have now your invariants. Yes? So I1 will be sigma 1, 1 plus sigma 2, 2 plus sigma 3, 3. Yes? And then what about this one? The sum of the square of your shear stresses. Sigma 1 squared, sigma 2, 3 squared, sigma 1, 3 squared. So these are the sum of your shear stresses. What about this one here? This one is the determinant of this one here. I1, I2, I3. So if you plug it in here, then you get this very nice equation here. Right? And knowing one root is 200, then of course you end up with a quadratic equation. You can now solve for the other two stresses. So please go through this one. I haven't had any problem with your seniors then. So I would think that there's no problem here. You will be able to follow this one if you go through this example. So this is your equation. Instead of solving this one to make life easier for you, you can have this equation. And then of course you can simply now determine your invariance I. Oh yeah, sorry, this one is the longer method. Okay? So from here, you will now be able to determine your principal stresses, knowing that you have one of the roots already. That makes it easier. There's so many ways to calculate for this quadratic equation here once you know this one. So many ways of doing that. One is, of course, if you have this equation, then you simply divide this one with this one here to get your quadratic equation. I think there are more simpler ways of doing that, and I've seen some of your seniors doing that. So it's not something that I have to tell students to do this and do that. Okay, so here, we have now the other stresses to be 700 and negative 400 megapascal. Let me write it down. So once you know this one, then you can solve that. Let me remove that. And you have sigma 1, sigma 2, and sigma 3. This will be 700 megapascal. This will be 200 megapascal. And then we have a negative 400 megapascal. Now again, I'm just using the results from your lecture notes. So feel free to calculate, and you can check whether the solution or the numbers here are correct or not. Yes? So after solving for sigma 1, sigma 2, and sigma 3, the question asks for that track length, A. So how do we do that? Well, the equation is already given, so we don't really have to bother much about what equation to use. So we have now here sigma 1 pi A must be less than or equal to the fracture toughness. So we just equate this one to the KIC, or the fracture toughness, equal to 24 megapascal square of a meter. And then since we have this one here, then we can now determine that length of the crack. Yes? So if you want to check the units, that's quite simple. This one is 700 megapascal. And then that's pi A equal to 24 megapascal square of a meter. So megapascal cancels out. Then so yes, right? So what will be your crack size? So as you can see, it's now in a meter. So again, the answer here is given to be 0.38. So I'm just taking the answers from your notes. So what does that mean? Okay. So if you have this length of a crack, any size larger than this one will cause this crack to grow. So any crack longer than this one will cause this one to grow further. So if it's smaller than this one, that's fine, it's not going to grow. But any length longer than this one, then it's really going to grow. And then failure occurs. That's why this is one of the criteria wherein, say for example, for every material, you assume a crack size that can be safe to be there. And then from there, you can simply calculate if you know the stress, you know your crack size, then you will be able to know your stress intensity factor, which must be lower than your fracture toughness. That's one criteria. So let's do this one the opposite. I have a crack. Let's use the same problem. I have a crack. So this one is say lower. Let's look at the lower value, 0.4, 0.3 millimeter. So that's the half length of my crack. And then I know my stress to be 700 megapascal. So my stress intensity factor is equal to sigma 1 square root pi a. Yes? And then this one is 700 pi multiplied by, so this one is megapascal, okay, Newton per millimeter. And then I have this one to be 0.3 millimeter. Okay? So let's check the units. Newton per millimeter squared. And this one is, or just megapascal, sorry. Megapascal square of a meter. So we have to divide this one with 1,000. Okay? So that's your stress intensity factor. So what's your stress intensity factor if you calculate it? What's this value here? Anybody? What's the value? So this one is 21.5 megapascal square of a meter, square root of a meter. Now, our failure criteria is that this one, this stress intensity factor that's acting on our material must be less than or equal to your fracture toughness, KIC. So 21.5 is less than 24. So we know that this one is safe. So anything larger than 3.8, we know that this SIF or stress intensity factor will be greater than 24, so it won't be safe. Okay? So that's one failure criteria that we're looking at. Aside from, this one is just static. We're not looking at fatigue at the moment. So you have sigma 1, von Mises, you have your stress intensity factor. So these values are used to be able to determine whether your material, your design, or your structure will be safe. Any questions with that? So we already have 3 failure criteria. So what's the purpose of mechanics or solid mechanics and finite element? It's just determining all these values, stresses or stress intensity factor and so on. thickness. So really, design is not just coming with good figures, very colorful, very colorful structures and so on. You have to check that your material must not fail or your structures must not fail. Okay. Questions so far? So we were able to solve one problem now on fracture mechanics. So we have pre-failure criteria. This one is in chapter 24, I think. So I'm just... Yes, it's in chapter 24 of your notes. It's mixed in finite element, but this is also in Moodle. I placed this one in our Moodle. Chapter 24, 24.16, special topics. Yeah, for some reason it has been mixed with finite element, but I really want to take it out and then discuss it together with elasticity here. Any questions so far? Let me try to just discuss what we have discussed earlier. We have now this multi-axial state of stress, stress states. So we have your state of stress, and then you can actually determine your principal stresses. So the thing is that the challenge here is determining your state of stress, and actually you can further simplify that using the analysis. So in this case, for a beam bending, okay, your sigma 11 is that stress due to the moment, and your shear stress is F all over A. For pure torsion, you only have shear stresses, you have zero normal stress. So what about pressure vessels? Let's try to look into this one here. Let's try to derive the equations. So we have two types of stress. One is sigma theta, and the other is sigma xx. Theta is the circumferential stress, or the so-called Hooke stress. So Hooke stress, the stress will be acting around the cylinder, while longitudinal stress will be acting along the length of your pressure vessel. So we have two stresses acting here. One is Hooke, and the other one the longitudinal. Yes? And let's try to derive these equations, and then from these equations that we will be able to derive, let's try to determine which one is the critical stress. So how do we start this one? Small element? We'll have the small element later for thin pressure vessels. So we're looking at the moment at thin pressure vessels or thin-walled pressure vessels. Now there's the criteria for thin-walled pressure vessels, wherein we have the D, or the diameter of your pressure vessel, and the thickness of the wall. There's a criteria so that here our inside diameter is approximately equal to the outside diameter. meaning that the thickness of the wall is thin. Okay, so there are cases wherein you have the R radius all over the thickness is greater than or equal to 10. Then you're allowed to use this one. Sometimes this can be 20. Or probably D all over the thickness is greater than 20. Or 10. Some are even using D all over T greater than 10. So I don't know what your nose is using at the moment. So you can have a look. So here you have a thin-walled pressure vessel wherein we want to know the stresses acting on this one. So how do we begin with this one? So we use the principle of statics. Equilibrium of forces along the longitudinal direction is equal to 0. So you basically have it here already, but let me try to. For example, that is your. Yeah. Okay, let's do this one. Yes. So this one will be your. We're looking at the end of your. We're looking at the end of this one here. Or you can say here, longitudinal. So at this one here. So this one will go around there. So you have now a sigma ZZ. Right? And then you have now your pressure here acting. And this one will be your diameter. Yes? So there will be a thickness here. So there's that thickness T. So all we have to do is take the summation of forces along the z-axis to be 0. Yeah? And then this force here caused by sigma z. So knowing that stress equal to force multiplied by the area or divided by the area, your force is sigma multiplied by your area. So here sigma z and the area that it's acting upon, what's the area? So that's the circumference multiplied by that thickness. Right? Pi dt. Yeah? Or 2 pi RT. It's there already. It's there already. Yeah. So this one is either. So let's look at this one here. Sigma ZZ multiplied by the area it's acting upon. This one now will be pi d multiplied by the thickness, or in this case, it's given to be sigma ZZ multiplied by 2 pi RT. Yes? And what about this pressure here? So you have this one, all the pressures are there around that diameter. And the area. So your area will be basically the area of that solid circle. wherein you have that pressure acting upon that area. Pressure, take note, is also a unit of stress. So pressure multiplied by that area. So the area, of course, is the area of the circle. While that sigma z is just acting on that thickness around. Right? While the fluid or whatever gas you have inside the pressure vessel will be acting upon that circular area. So that we have this one to be minus the pressure P multiplied by the area, which is pi squared or pi over 4 d squared. Right? And of course this is equal to 0. So from here we will be able to get the sigma z. So this one is P d all over T, or you can have this one to be, sorry, that will be d all over 4T, or this one will be P r all over twice the thickness. Yes? So that is just for the sigma z. So what about the other one? That's got the drawn half cylinder. Yes. So what will happen here? Okay, so this one now is a hoop stress. We're talking about this one here. Yeah, we're looking now at the hoop stress. So this part now here. Okay, so you have now here your hoop stress sigma theta theta. And then of course you also have your pressure going there. You know that pressure distribution. So you have this one to be P. Yes? And say for example you have this one to be L. Okay? Or for this example it's called DZ. So DZ. Let's do that.
0, 0,
So we have this one to be your thickness. Yes? And then here, again, if this one will be your y-axis, you're taking the summation of forces y equal to 0. So the summation of forces y equal to 0, so what happens? So your sigma z multiplied by the area is acting upon. What's the area? So assuming that this one is the length. Okay, let's use dz. Yep. So let's use dz. Two times dz t. Okay. This area here, this solid section. That solid section that stress is acting upon. And then what about the other one? Minus the pressure. What will be the area it's acting on? So assuming that is your diameter. So the pressure will be acting on this area. Length multiplied by, or dz, multiplied by B. So this now is equal to 0. Yes? So that is 2 there. So what do we have? Dz cancels out. Sigma theta theta is now equal to ED all over 2T. Yeah? And this one can be what? ER all over T. Derived using first principle, no magic here, no analysis here. Of course, we haven't gone to the thick pressure vessels yet, which we will be going later. Don't worry about that. That's where your small element will come in again. So let's have a look at this one here. So you have your hoop stress acting on this one, acting around the hoop, and then you have your longitudinal stress acting about the neck of the pressure vessel. So let's write those two equations. Yes, so which one will be greater? Theta theta or Z Z? So the value sigma theta theta will be greater than sigma Z Z, right? So it's more critical. So that the design of the pressure vessel will be mainly based on sigma theta theta. Yes? So this is for inward pressure vessels. Now, this one is already in Moodle, so you can, I think it's there already, so you can simply download this material. There you go. So these are the definitions, and then where does sigma ZZ and sigma theta theta, if we're going to take a small element? This will be your hoop, and that will be your longitudinal, which is sigma ZZ. Right? As you can see, they are acting normal to these surfaces or these lines. So basically, they are normal stresses. We don't have any shear for this particular moment or this particular application. No shear, only normal stresses. So if you fill in your state of stress, it's this one. So have a look. That is your hoop stress, which is PR all over T, and that will be your longitudinal stress, PR all over 2T. So if you write them, your state of stress is your two normal stresses and no shear, 0. So this will automatically be sigma 1 and the other is sigma 2. Reason because there is no shear, so they are automatically your principal stresses. Sigma theta theta being greater than sigma ZZ will automatically be your sigma 1 for your first principal stress, and the lower one will be your second principal stress. So why is it 2 by 2? Because it's a thin structure. We're using the plane stress assumption. Of course, if we're looking at thick wall pressure vessel, we will be including the 3 stresses. Okay? Any questions so far? So that's how you come up with your state of stress. So we already done that with the beam. We have done this one. We have done it with these pressure vessels already. Of course, other structures are more complicated. So these are just examples. Attendance, please. don't normally get them. I don't know why.
Rồi mới đi không phải girlfriend. Chị là cô à?
I saw
So how about let's have a 10 minutes break?
already.